This is Baslercast, tutorials for Mr. Basler's physics class. This video is about acceleration for one-dimensional motion. Let's take a look at a few examples. Acceleration can be a little tricky sometimes, particularly because of the direction. So let's start off with a velocity versus time graph, and let's start off with the type of acceleration we're most familiar with. This is an object that was going at some predetermined speed and now has sped up over a period of time. And we can find the acceleration for this particular situation by knowing the amount of time it took and the actual change in velocity that took place. So that's a simple equation that says that change in velocity divided by time equals acceleration. So let's substitute in some numbers here. Let's say that our change in velocity is a 6-meter change. So maybe it's going from 3 meters per second all the way up to 9 meters per second. So we get a 6 meter per second change, and let's say that happens in 2 seconds. Well, then this acceleration here would be 3 meters per second, which is to say that every second that goes by, the speed increased 3 meters per second. Now, if we spun this graph around a little bit and looked at it from a different perspective, let's say going down, still in the positive, what's happening now? Well, now we'd probably drop from 9 all the way down to 3. So now we have a negative 3 meters per second because the change in velocity would be negative over 2 seconds, negative 6 over 2 seconds. Another way to think about it is, hey, this slope is negative. So if it's a negative slope, it's a negative acceleration. Now what if we slid that down into negative space? Well, it's still a negative slope, so the acceleration is still negative 3 meters per second because it's, in this time, going from, let's say, negative 3 up to negative 9, and so that's a change of negative 6 meters per second. If I flipped it around down in the negative, now we get a positive acceleration. Notice the slope is positive, and that's because maybe we're going from negative 9 meters per second up to, or slowing down to negative 3 meters per second, and that change is a positive change. It's a positive 6 meters per second in 2 seconds. And so that's kind of to tidy up the directions of accelerations. Now let's try something a little bit more difficult. Here is a typical motion problem that involves an object that is traveling at a constant velocity and spending some time experiencing an acceleration. In this problem, a bird is flying south for the winter. It is airborne and traveling at a constant velocity for 9 seconds when it is struck head-on by a gust of air that causes it to experience a constant acceleration of 2 meters per second. The gust of wind lasts for 6 seconds, after which the bird's velocity is negative 5 meters per second. If north has been chosen as the positive direction, how far has the bird traveled? So I like to set these problems up first with a simple picture. And so I started off with north being the positive direction, as you see here, and south being the negative direction. And our bird is flying towards the south, like all birds do before winter. And we don't know what that constant velocity is in the beginning. It travels at that constant velocity for 9 seconds, as the problem outlines. Then, after the 9 seconds, it encounters the gust of wind, which is called a which causes a 2 meter per second acceleration. Now, the picture helps us understand that even though this is a 2 meter per second, it's a positive number, that this is causing the bird to slow down. Since the initial velocity is negative, the 2 meter per second acceleration causes the bird to slow down because it's in the opposite direction of the bird's motion. So after the gust of wind, we are told that the bird is now going at negative 5 meters per second. So it's dropped all the way down from some speed, which we need to find out, to negative 5 meters per second. So the next step, after you kind of get a good visual for the problem, is to think about what a graph of this problem would look like. So we know that all the velocities are going to be spent in the negative space. We're going to start off with that initial period of 9 seconds at some constant velocity. And then after 9 seconds, it's going to have a period where it slows down. And this is the positive acceleration of 2 meters per second per second. You can see that it's a positive acceleration because it's a positive slope. Now it's slowing down, but when you slow down in the negative, you get a positive slope. You get a positive acceleration. So we know what this value is. We know that it ends at -5 meters per second, but we're really after what that initial velocity is. That's the thing that we don't know. But fortunately, we know acceleration is taking place here. And since we know the equation for acceleration, we know that final velocity minus initial velocity, or change in velocity, divided by time gives us acceleration. We can do some algebra and rearrange and solve this initial velocity. So rearranging this equation, we can solve for initial velocity. Substitute in the values for final velocity, which is -5, and acceleration, 2 meters per second, and the 6 seconds, we're able to determine that the initial velocity is -17 meters per second. So we can change that on our graph and have a more accurate graph to move forward to find how far the bird traveled, or its displacement. So let's look at that next section. Well, there's a couple ways you could go about figuring out the bird's displacement. You could shade in this entire area and say, okay, I'm going to break this up into a little rectangle, a big rectangle, and a triangle. And that's perfectly fine doing that, and I recommend that. I don't think that's a problem. But I thought you know how to do this and you had some experience in this process, so why not think of it a different way? Why not think of it in 2 steps? Let's figure out what this entire rectangle is and then just subtract this little rectangle. And that can be done like this. You could take the initial velocity times the change in time, and that would be the entire change in time. So that would be the full 15 seconds, and you'll see when I substitute the numbers in. And you're going to add 1/2 change in velocity times the change in time, and that would just be for the 6 seconds, the period where it's accelerating. That would be this little triangle. Actually, it would be this triangle, but you can see that it would be the same side. So if we substitute in our numbers, we'd have -17 for 15 seconds, and that would give this whole big rectangle right here. And then we add 1/2 times 12 meters per second times 6 seconds. Okay, so that's because this acceleration period lasts for 6 seconds, and -17 up to -5, that's a change of 12. So if you do the math here, you wind up with an answer of -219 meters. And that's how far our goose traveled, 219 meters, but that would be in the negative direction, hence it's traveling south. Happy winter, goose. And that's it for this tutorial on all things acceleration for one-dimensional motion. I hope you enjoyed it and found it useful.